Good afternoon, everybody. It is with great pleasure to introduce today's speaker, Dr. Syksy Rasamen from University of Helsinki. He is a, I would say, early universe cosmologist, late universe cosmologist, and for a brief period, particle physicist when he was at CERN. I think you got a PhD in University of Helsinki, is that correct? Yeah. Then postdoc was in Oxford, CERN. That's as far as my memory takes me.
Oxford, CERN, University of Geneva, and then I had brief periods back at CERN, the Washington University, St. Louis, University of Chicago, LA, PhD in NSA, and then back to Helsinki.
Yeah, well, yeah, as long as I've known you, you've been in Helsinki, so welcome, and yeah, Syksy is available today and tomorrow, hopefully, as well, for discussions, and he's going to talk to us about primordial black holes.
Thank you. So please interrupt me with questions as much as possible. So I'm going to talk about some work that I've done with Dani Figueroa. Dani Figueroa, Sami Radikon, and Emily Tuberg. So when we started, Sami and Emily were both my PhD students. Emily is now Lancaster, moving to Belgium this fall. Sami actually after getting his PhD, he didn't want to continue in academia, so he's now working as a contractor for BMW for doing machine learning. They want to design algorithms that would design cars. But he said that the private sector stuff is so easy that he's still doing physics. Actually, he's still doing stochastic inflation, as a hobby with the same level of intensity as doing his PhD. Just for fun.
Maybe you don't want to say that to his employers.
So, so there are hundreds of models for what particles dark matter could consist of. But there's also a possibility that dark matter doesn't consist of particles at all. That there is no new particle, no new field associated with it. And this possibility is that dark matter could consist of black holes. Has become very popular recently, just because, I think just for sociological reasons, just because of the LIGO-Kagla observations of black hole collisions have brought black holes back to the forefront. But this was already suggested by Hawking more than 50 years ago. So Hawking observed that if we look at the density of baryonic matter in the universe, we basically have the right numbers already in 71. He noticed that if you look at the clusters of galaxies, this is not really enough to make them gravitationally bound. And if you look at the overall density of the universe, the baryonic density, there's a mismatch. So you could have extra matter that could, so dark matter that could consist of black holes. And more recently, there is another reason to consider primordial black holes, which is that the fact that as we with new observations, the James Webb Space Telescope, and already before that, but now increasingly so, we see more massive galaxies at earlier and earlier levels. And it's beginning to be difficult, more and more difficult, to explain how these massive black holes have formed. Like, how do you form a black hole of 100 million solar masses in 100 million years, or less than 100 million years? And so one possibility is that you start with a smaller black hole that was formed earlier on, and then the core of and then that acts as the seed on which the black holes at the centers of galaxies grow. If we want black holes to be dark matter, then there's actually many ways of observing them. So this is a plot where you have the black hole mass in solar masses here and here in grams. For some reason, people like to use grams here. And this is the fraction of dark matter that is in primordial black holes. So the most relevant constraints are evaporation and microlensing. So if we have primordial black holes that are massive, then when they pass between us and stars in the Magellan Cloud or Andromeda or some other nearby galaxies and dwarf galaxies, then we see an extra shrinking of the stars in those galaxies. This twinkling is not seen, which then restricts, cuts off these higher masses. And when you get to about 10 to the minus 11 solar masses, then these constraints go away, and they go away mostly just because it becomes too difficult to treat the finite size effects of the stars. And then lower masses, so there are good reasons to believe that dark holes evaporate by Hawking radiation, and then if they're on this line, we would see the evaporation right now, which is not seen. And if they're less massive, then they would have evaporated. So there is some mass window between about 10 to the minus 11 and 10 to the minus 15 or 16 solar masses, which is the asteroid range. And then there is another possibility that because of Hawking evaporation, dark holes, the evaporation stops, and you have these Planck scale relics. So that would be the Planck mass quiz. How many people know what is the Planck mass in grams? Nobody. It's 1 microgram. It's about one mode of dust. So that would be here. So there we have lots of space opening up because you just evaporate out of the Planck scale. So these are the two possibilities, asteroids and Planck scale, and I think the Planck scale relic is actually physically more interesting, but now I'm going to talk about the asteroid relic case. It's also much more difficult.
So to understand, reading your graph, you're going up to a fraction, 100%, is that?
Yes. Yes, I want all of the dark matter to be black holes.
So you see a possibility that, you see, there's two regions where you can have all of it.
Yes, asteroids or these Planck scale relics. And
is that consistent with the bullet cluster?
Yes.
I've heard people just say that it isn't, so I'm just...
What do you think would be the problem? I mean, what you see in the bullet cluster is that you see that the dark matter interacts only gravitationally, unlike the baryonic gas, which is left behind. And if you want matter that interacts only gravitationally, then primordial black holes are much more accurately that than any particle dark matter. Because if you look, I mean, the physical size of these objects, so we call it solar mass black, like for solar mass, for the sun, the Schwarzschild radius is 3 kilometers. And the biggest that these are 10 to the minus 11, so that's 10 to the minus 8 meters, that molecule size. And when you go down here, it's subatomic size. And for Planck scale, if you go Planck scale relics, of course, it's the Planck scale. So physically, these will never collide with anything. They're way too small. And they only have gravitational interactions. Whereas, for example, if you take WIMPs, they will have non-gravitational interactions, which are, of course, weak, but not as weak as these. So this is much better called dark matter than WIMPs. Good. So now to generate black holes, you need large fluctuations in the mass distribution on small scales. As mentioned, the biggest of these are like molecule size. Natural possibility is that you could generate these large fluctuations on small scales by the same mechanism that generates the known small fluctuations on large scales that acts as the seed of galaxies and that we see in the cosmic microwave vacuum. And objectively speaking, the most successful scenario for this is cosmic inflation, and subjectively speaking, I would also say that it's the simplest of all the proposed scenarios. And how to do this in inflation is very simple. In inflation, the relevant parameter is the curvature perturbation. And if you consider slow roll inflation, you need to go beyond to fix the ideas. Then the scale of the curvature perturbation is given by the Hubble parameter times the typical filter deviation from the background in the field times the background time derivative of the background field and typical deviations of the field perturbations of the Hubble parameter. So the typical curvature perturbations of the Hubble parameter squared divided by phi dot. And during inflation, the Hubble parameter is about constant. So to get large perturbations, you need small velocities. So the slower the field moves, the bigger are the perturbations. So now the idea is very simple. the field moves slowly during the period of inflation when you generate the CMB perturbations, and then you need to make it move even more slowly to generate in a different region of in a different part of the potential to generate even bigger perturbations. So it's just a question of what is the form of the potential. So once you so during inflation you generate these large homogeneities and nothing interesting happens to them during inflation. The reason is that you generate perturbations that have a large amplitude, but because of the accelerating expansion, their wavelength is pushed beyond the Hubble scale, so they freeze. So you have large perturbations that they cannot collapse because the wavelength is so large, and you have this Hubble scale basically sets the range of causal interaction. But when inflation ends, these modes keep stretching, but the Hubble radius grows even faster, so they cross back inside the Hubble radius, start evolving, and if you have big enough overdensity, then they collapse. And if you have enough mass, then you collapse into a mass overdensity, you collapse into a black hole. So a simple idea of this is that you have one wave number, you have some overdensity. Once the wave number crosses back into the Hubble radius, the whole Hubble patch collapses into a black hole. Of course, the real situation is more complicated, and the collapse process can be quite involved. And you have a distribution of different Fourier modes, obviously. And the typical primordial black hole's mass can be like 10% of the mass inside the Hubble patch or something. It can vary, but the basic idea remains the same. So what do you need to do? And then once you have these primordial black holes, you want to know how many of them do you have today. So there are two effects. This depends on the black hole mass. So obviously, if you generate some number of black holes earlier. So obviously, the bigger is the mass of the individual black hole, the bigger is the energy density, because you have more mass in them. However, the bigger is the mass of the black hole, the bigger is the Hubble radius when it collapses. So what happens during inflation, these modes cross out of the Hubble radius, and then when the Hubble radius starts growing, the smallest modes cross in first, and then the later modes cross later. Which means that the smaller black holes form earlier, and once they form, as mentioned, they're like cold dark matter, so the energy density is like just 1 over the volume, 1 over a cubed, while the radiation energy density, because this one the universe radiation dominated, goes like 1 over a to the power 4. So the relative energy density grows. And the earlier you form the black holes, the more time you have for them to grow, and it's actually this effect that wins. So if you put these two effects together, what you basically find that the primordial black hole density today, so observed, this is all the dark matter, this should be about 0.3, is about 10 to the 7 times the mass divided by the solar mass to minus 1/2, and then beta is just the number density of the initial number density of the primordial black holes.
And what sort of distribution do you expect for the mass?
Right. So I'll come to the mass distribution. Typically, the mass distribution is... Okay, the honest answer is that the mass distribution is quite complicated because there are different effects that feed into it. I will discuss one effect later and I can mention some others. But typically, you will have a broad mass distribution. You will never have just single mass. This cannot happen. And in fact, there may be a problem fitting the mass distribution into the observational window.
It's presumably skewed, maybe skewed towards larger masses or something.
There are different effects, but let's discuss that when we come there, because there is an effect that skews it towards large masses, and there's another that pushes it to low masses. So let me just thank you. So the idea is now that this beta is the initial fraction of primordial black holes. So we consider, these different patches of the universe, that evolved in stages like the Hubble, this type of Hubble patches, and the beta is now the number of the fraction of the Hubble patches where the mass over abundance is so large that you form primordial black holes. And you see in this kind of stuff. Thank you. So you see that the heaviest black holes that you have are 10 to the minus 11 solar masses. So these are 10 to the 6. So this beta initially is 10 to the minus 14 or smaller. This number, so you need to have very few black holes in the early on, otherwise they would dominate too soon. This is a problem for numerical analysis of this, which is what we have done, because you need to probe very far into the tail of the distribution. So you need to either have lots of computing power, which we had initially, and which we still have, or be smart. Then we also tried later being smart.
Now, how model dependent is this value of beta you're referring to?
Both of these numbers are extremely dependent on the model. So if you have an evaluationary model, then the mass, as noted, is just basically, in the simple picture, it's just determined by when these perturbations cross back into the Hubble radius, which just depends on, so it just depends on at which part of the inflationary potential do you put the feature that slows down the inflation. Now we show you a potential. So that's basically just what field value do you put this feature in potential, and this beta is then determine how strong this feature is. How much do you slow down the field? If you slow down the field a lot, you generate big perturbations, and then you generate more vacuums. And the abundance is very, very sensitive to the features and potential. Good. Other questions about this? So let me just outline what is basically done. So what is the simple way of calculating primordial black hole abundance, and then explain how we have gone beyond this simple treatment. So one is to just basically write down a potential where the field slows down. I'll show the potential one of the potentials we have been using. Then you solve for the background field. So just put this potential in your differential equation solver. Then you get what is the background field, and then you just calculate the linear perturbation theory. Just calculate how the linear perturbations happen. You get the power spectrum of the perturbations, and this gives you the variance in patches of sizes kTBH. So if we would have one scale for the black holes, this would be the scale kTBH. And then if you integrate the power spectrum up to kTBH, then this is some infrared cutoff, just like the size of the present universe today doesn't really matter. Then it will tell you what is the variance, of in this distribution of patches. And you know that in the linear theory, the distribution is Gaussian. So then you just have, you have a Gaussian distribution. Variance tells you the mean of the distribution, and then you just find the initial black hole abundance. You just integrate. So here you just have the threshold for collapse. So you say the curvature has to exceed a certain value, and if you exceed this certain value, then you will collapse. And then you just integrate this distribution, and this gives you mean. So this is and if you do this, you can write black hole papers very easily. And there are many black hole papers like this. And also for initially me and Emily, this is what we did initially. I mean, our idea was we wanted to use the standard model. So use only the standard model with the nominal coupling for the Higgs to gravity, and then look at the quantum corrections and see can we fit both the C and D non-primordial black holes with just the Higgs, nothing else. Turns out you can do it for relics, but not for the isotopes.
That means, what does that mean? It means you're trying to use the Higgs as an.
Yes, we use the Higgs as the inflaton. So basically, so then you can have also dark matter from the Higgs in a sense. Higgs that then decays and gives you the radiation bath, this radiation that collapses the black holes. So, but this is what many people have been doing and are still doing. However, there are big problems with this naive analysis. One, recall that to get these big perturbations, the field has to, which you need for the primordial black holes, the field has to move slowly. But because it moves slowly, stochastic effects can be important. And I'll discuss this in more detail in a moment. But this just means that the background evolution depends on the perturbations. I'll explain this in more detail in a moment, but you can understand this very simply. If you have big perturbations, they can have a big effect on the mean. This is very easy to understand. And even if the mean is not strongly affected, primordial black holes are very rare. So actually you're sampling really the tail of the probability distribution. So even if you have small corrections, they can be important. And what actually happens is that you have a correction that is exponentially small. But if you compare an exponential and a Gaussian, the exponential wins very quickly. So you need to be able to calculate these as exponentially small terms in the tail of the distribution. Okay. The second is that actually the value of the curvature perturbation does not correlate with the formation of primordial black holes. So people have done these numerical simulations for many years now. So you have a radial, you assume radial symmetry. spherical symmetry, and then you just have put some stuff, some density profiles, and you check, do you form a black hole or not? And then you see what are the properties of this density profile that actually correlate with whether you get a black hole or not. And this zeta does not correlate. And the physical idea is just that this curvature is much more sensitive to long wavelength modes than the density, and collapse depends on the local fluctuation. You know, it's just that the overdensity is like lambda squared times the zeta, the curvature perturbation.
And at what scale do you start the inflation?
What scale do we start calculating things?
Or do you start before the Planck scale?
What do you mean by you mean the field value or the field value is super Planckian?
It's field value super Planckian.
Yeah.
And
but the energy density is of course way below the Planck scale.
Well,
but it doesn't really matter where you start.
There's a scale that should be relevant there. When you exit inflation, how many foldings have you? I'm sure it's probably the equivalent.
Let me show. Okay, maybe it's best if I show this. So this is the inflationary potential that we're using. So this is the originally we studied in the heat stream, which is that this is the phenomenon coupling to the Ricci scalar, but I don't really want to talk about where this is coming from, because you could just say I pulled this out of my hat. There we were interested in really what's happening with the real Higgs. Here I'm more interested in if you have this type of potential, what happens.
Did you say minimal coupling?
Non-minimal coupling. So basically you have the Ricci scalar times the field squared.
Yes, and you put some parameters.
Yeah. So now, what happens is then you have this asymptotically flat region, and this is so that you start somewhere. It doesn't really matter where you start, because it doesn't matter what is the total number of e-folds. This is completely irrelevant, because this is unobservable. What matters is what is the number of e-folds between when something happens and the end of inflation, not the total. So this is the CMB region, which is about 50 e-folds before the end of inflation. So the field rose here, rose very slowly because this is flat. Then, because of quantum corrections, this becomes less flat, the potential, and then the field goes down rapidly here. And then we have a local minimum, local maximum here. The speed slows down, and you understand that you can actually make it go as slow as you want by just tuning. You know, if you tune it so that it doesn't make it out, then velocity goes to zero, and so make it a bit lower, and you can make the velocity to whatever you want. So the relevant scales are here. These field values are all about the Planck scale. This is like 5 and this is like 0.5. There's not that much difference. In terms of the physical scales, of course, there's a huge difference, the exponential expansion. But the relevant, so the size of the black holes is determined by where you put this potential. Because this determines where, during inflation, you form the primordial black holes, where you form these perturbations. So if it's very late in inflation, then they go out of the Hubble radius cross very quickly back.
So who's giving you that little bump? Because you're still.
This is a standard model loop corrections that give this bump. So this is completely standard model loop corrections. So if you really use only the standard model, then we would have to use the relic case. Otherwise, it's called the CMB region. Here we have taken the standard model and then just by hand made this flat.
And for what value of C do you get this shape? Is it still
I don't remember. You can adjust so the typical value of psi is 10 to the 4 when you don't have this loop correction. With the loop corrections, you can turn it down. Maybe it was 100 or something. I don't know. 100 or 1,000 or something. Anyway, I could just write, take pen and paper and write this. It doesn't matter.
Where will the Planck scale be on this?
The Planck scale in the field values, it's about here. But in my view, the value of the field relative to the Planck scale is completely irrelevant.
No, but I mean, just the quantum gravity era is somewhere there in the middle of your picture. But
no, the quantum gravity cares about the field value.
Why not? Of course it does.
Well, the field value is also framed.
It cares about the scale, if I can associate the time scale to it.
Yeah, but but it depends about the size of the energy in your fluctuations and the energy density. And both of these are well below the Planck scale. The field value is not that important. And then there's a different question that if you calculate corrections, what happens to this picture? So if you have higher order terms, in the potential or something, then that's a different story. But from quantum gravity point of view, it doesn't. I think it's irrelevant. Okay, and this, by the way, this has to be large field inflation, basically because, I think for anything realistic, because you have to be able to separate the CNV region and this primordial backbone region from each other. Typically, the problem is that if you do some log corrections or something, then in order to get this, you will also spoil this. So they have to be separated, and here it's not, I think this is 4 or 5 time scale, is about 4.5 or something. So they're separated. Even if field space, this is not a lot. And if you have small fields, then they're too close to each other. Okay, back on track. So we have these problems. One is that what I just described is, you just have the background evolution and then linear perturbation theory, and they're independent of each other. In fact, large perturbations can affect the background, and then this changed background evolution can affect the perturbations. The second is that the curvature perturbation does not actually tell you where the black holes form. Let me first discuss this first part, stochastic inflation, so the influence of large homogeneity. So all inflation is stochastic. It's just the statement. So stochasticity is inherent in using perturbation theory and splitting the background and the perturbations when your perturbations are quantum mechanical. So basically, this is just it's just taking into account the coupling between small and large long wavelength modes, as introduced Starobinsky in a landmark paper in 1986. So there are many technical details to stochastic inflation.
What's the difference between small and long wavelength? What do you mean by small?
So the wavelength compared to the Hubble radius. Do you have modes?
That's long wavelength, yeah. Okay.
Yeah.
What's small mean?
Small wavelength, less than the Hubble radius. Long wavelength, much bigger than the Hubble radius.
Oh, you're just using the two terms synonymously.
Which two terms?
Small and long.
No. Small means much shorter than the Hubble radius. Long means much longer than the Hubble radius.
Oh, I see.
Okay. So I just sketch out how this happens. So the idea is the following. You start with the Hubble radius. So this is one Hubble patch. And the Hubble radius is pretty much constant during inflation. And then you generate these quantum mechanical fluctuations, which you put initially in the sub-Hubble regime. Then at a later time, the universe is expanded, and then the wavelength has become much, much longer. So now, on the scale of this patch, this mode looks constant. And as you have a new mode that is generated, this new mode cannot distinguish between the original background and the background plus these old long wavelength modes. So this means that these long modes change the background over which the shorter modes evolve. And these inflationary fluctuations are quantized in momentum space. And they're basically drawn from a Gaussian distribution. Which means that now what happens is that you have this wave, and then it stretches. At some point we say it's part of the background. So then the background field changes. And the next instance of time, another mode joins the background. So the background is subject to these random kicks with drawn from a Gaussian distribution and white noise because the momentum modes are independent. And this happens. And this you cannot avoid. It's just the way that you split between your background and your perturbations. So this means that now the evolution of the background is not deterministic; it's stochastic with this quantum noise. And usually, for most inflationary models, this doesn't matter because the perturbations are small. CNV perturbations -5. So, and if So typically, they don't have a large impact, but now you have big perturbations and you have to worry about this. So what happens is here you generate these -5 perturbations, then you go down here, and then you generate the large perturbations when the field slows down. So, and the fact that the evolution is slow, is one of the reasons why stochastic effects are important. So typically for inflation, one considers slow roll inflation. You may have heard this term. If we discuss primordial black holes, we have to go here. Here's sort of a sketch. The actual equation of motion is more complicated, but here's a sketch. We've got an equation of motion with the acceleration term, the Hubble parameter, which is very constant, so this is the Hubble friction term, that's force counter field. We have the classical force given by the derivative of the potential, and then we can have a stochastic noise. So slow roll inflation is the regime in which the acceleration is 0. So you can neglect this, and you have a balance between the friction term and the force term. So this is like parachuting. So if you drop from up, high up with a parachute, eventually you reach terminal velocity. Actually, if you're high enough up, you don't even need a parachute. So when your velocity becomes constant, so the gravitational pull and the friction balance each other. So this is slow roll inflation typically. Ultra slow roll is something else. It's when you are very flat potential or you're close to a minimum or a maximum, so you can neglect the derivative potential, so you have 0 force. So this is like sliding a brick on a flat surface. There's no driving force, so you see, if you neglect the noise, you see here that phi dot force h is constant, falls exponentially. The velocity falls exponentially, and this also means that now, because there is no, the force term is small and the velocity drops exponentially, the velocity drops, perturbations become large, and this kicks can also be, quantum kicks can be important because they don't have to compete with the classical force. So the way stochastic inflation is done in practice is just you take the incident field, so you have this is the full field, no split to background perturbations here. You write it in Fourier space, and then this is the decomposition that you have some, so AH is just a co-moving Hubble radius, and sigma is some number that tells you at which point do you take the perturbations to have joined the background. So you cannot take them at the Hubble radius, you have to take them at some longer scale, and then technicality, basically, when do you consider the mode to become classical and join the background? Typically, the sigma is like a 10 to the -2 or something. It's about 100 Hubble. So the modes that have wavelengths longer than, let's say, 100 Hubble radii are your background. So now the background depends both on time and space, of course not homogeneous. And the modes then that have the longer, that have shorter wavelength, bigger wave number that are still inside, they are the perturbations. So now you have a system and environment, and your system is the long wavelength modes. And the environment is the short wavelength modes that provide this quantum modes. So you have a constant flow from the environment to short wavelength modes into the system. And as modes join the background, they give these quantum kicks, which give this white Gaussian noise, and the mean amplitude is determined by the power spectrum of the perturbations. So this looks like very simple, but the stochastic method is very powerful. So it's not, so obviously this is non-linear because it involves mode coupling, but actually you can even calculate non-perturbative results with this. So if you take, for example, lambda phi to the 4th theory, and you calculate just the in correlators, so I calculate the loop corrections to this, and you can, then you have in the loop corrections, you have these corrections that are logarithmic in the scale factor, so you have things that grow in time, and they have been calculated to 2 or maybe 3 loops during inflation. And with the stochastic formulation, you can calculate the full series, the leading logarithms of the full series, and you can resum this full series. And if you compare the coefficients in the series, they don't match approximately, they match exactly what you get from the loop calculation. And from stochastic formulation, you can also get results which go like 1 over lambda.
So what do you mean by the stochastic formulation?
So basically you this that you just use you take this equation of motion. Well, actually it's more complicated than this, and then you split into long wavelength and short wavelength modes, and the short wavelength modes you move to the right hand side, which become the noise, and then you just calculate what are these kicks giving you, and you just have a Langevin equation, which you can turn into a Fokker-Planck equation, and then you just solve the Fokker-Planck equation, and then you get the result which agrees with these loop computations. I'm just mentioning that to say that there's sort of evidence that this makes sense, that you can check the results from this simple thing actually leads to something interesting. So again, field is rolling here, we generate the CMP perturbations here, go down here, the noise becomes important, the kicks are important, and you will generate the primordial. So here you're in slow roll, and once you come here, you will go to ultra slow roll, because here obviously at the minimum and the maximum, the potential, the first derivative potential vanishes, and if you're close enough, the first derivative is small. And the power spectrum that you get for the curvature looks like this. So this is the amplitude of the power spectrum, logarithm of 10. This is the wave number. So this is basically this is the CMP region. So this is slow roll. So basically the power spectrum is close to scale invariant, amplitude of 10 to the minus 9. Then you have a dip, and then you have ultra slow roll. So the field velocity falls, and the power spectrum goes to 10 to the minus 2 or so. Then you come out of ultra slow roll, and the power spectrum goes. And it's this peak in the power spectrum that then gives you the large kicks, that will then give you large effects of primordial black holes, but also large effects of stochastic perturbations. Now, this story the calculation is a bit involved, because the background is affected by the quantum kicks, but also the quantum kicks. So the background is the quantum kicks, but the background also tells you how the quantum kicks evolve. So what we did for the first time was to really calculate both of these effects at the same time and see what's going on. So what we do is we write equations for the background, equations for the perturbations that are living in this background, and then we, of course, we start the simulation, then we stretch these waves, then when the first wave reaches the coarse-graining radius, we add it to the background, we change the evolution equation for the perturbations for the new background, we go one time step, we have a new mode, and so on. So we evolve this coupled system of background and perturbations for one patch. We continue until inflation ends, and we recall how long did inflation last. And this duration of inflation tells you the curvature perturbation. And we repeat this 10 to the 11 times to get statistics. Basically, we have 10 to the 11 different patches. Because these black holes are very rare, you need to have lots and lots of runs. And then we have the distribution. I mean, we find the mean of these. So in every patch, inflation has lasted a different number of values, different number of defaults, different amount of time. So that's why the different patches have slightly different curvature and slightly different density. So we find the mean, we subtract the every n from the mean, and this delta and deviation from the mean just gives the curvature perturbation. So this is quite simple. And this is the result. So this is the probability of given number of defaults, this is the given number of defaults, and this is delta and so deviation from the mean. So this is the full result, the blue one. If we fit a Gaussian, you see that there's no difference in the mean. Gaussian is this one. But if we say that okay, black holes are formed and the curvature perturbation is 1, not an unreasonable number, then basically when this is 1, there is a factor of 10 to the 5 between this exponential tail. You see that this is linear here on the log logs, on this logarithmic scale, and the Gaussian. So you see that this exponential tail enhances the black hole abundance by a factor of 2 to the 5. And this existence of the exponential tail was pointed out in 2 papers before. With the first one, we found it numerically, and we also found the full distribution, so see how you go from a Gaussian to an exponential. So if you want to find out how many black holes there are, in this asteroid mass case for this potential, you really need to take into account the stochastic effects. You will be completely misled by the abundance if you don't. So that's nice. Questions at this point? So we spent 1 million CPU hours to produce this picture. Unfortunately, it's completely useless for determining the black hole abundance.
So just,
yes.
You're saying that the distribution on the right-hand side of the maximum, at least, is just an exponential or quadratic with a linear term?
So you mean this shape of this probability distribution?
Yes, and if I take the right-hand side where it's linear,
yeah.
From the maximum to there, it's described by an exponential with a quadratic and exponential with a quadratic and linear term.
We didn't actually fit that, but I think,
that's what your exponential tail is.
Yeah. So we didn't fit that. There are also arguments. So later, or I should say, Emily was smart and found a way to get the shape of this distribution in a much simpler way, without having to do this brute force Langevin equation calculation. And to some approximation, it's an exponential with a linear and quadratic term, but in fact the exponential structure is more complicated.
The exponential
structure is more complicated.
Yeah, I can see that it is from the left-hand side.
Yeah. So it's not just so asymptotically it's exponential, and here it's Gaussian, but in between it's more complicated. It's not just a linear plus quadratic.
Yes, but if I take values larger than the if I take larger values,
then it will be an exponential. And also analytically, what's shown in these papers that basically, if you just go far enough, you will have only one exponential that dominates. Everything else is died away. You can write it as it's basically like these stochastic corrections are like one way to look at them is that if you're far enough, is that you have a series of exponentials, and the coefficients in the exponentials are the solutions to a certain eigenvalue problem, and then you just pick basically the one with the smallest argument. Okay, so unfortunately, you cannot calculate the primordial black hole abundance on this because this delta n, so the difference in how long inflation lasts, which determines the curvature in these patches, does not tell you whether black holes form or not. So then we thought, okay, maybe we should solve this problem. So if you look at these simulations that I mentioned, is that you have put different densities, spherically symmetric, see if they form a black hole or not, see what's the determining factor. Then it was actually shown that it's the so-called compaction function, which is 2 times Newton's constant times the mass excess divided by the radius. So you of course recognize that this is 1, then this R is just the Schwarzschild radius. And what typically happens is that you will form the perturbations will collapse. You don't need to start with the Schwarzschild radius. Typically, if the maximum of this C in the initial conditions exceeds some threshold, which is between 0.4 and 2/3, depends on the shape of the profile, then you will collapse the form of black hole. If you don't exceed this, then you will collapse, but you will collapse initially, but then the pressure gradients will win, and this overdensity will disperse. But there's quite complicated and interesting dynamics in the collapse. And I'm not going to talk about this in detail, but also if you look at the spatial average of C, so if you average over some regions, then it may be that actually this is an even better indication than the mass excess itself. So what we wanted to do was then to find this compaction function for every single patch. And to use this, then we need to have not just the value of here we have like the value of the curvature on one scale, which is the size of the patch. Now we need to have it as a function of radius for every patch. So this is of course computationally even more demanding, because now you need to resolve not just into the 11 patches or something, but the substructure in every patch. So we developed when we say we, I should mean Emily and Sami, developed a better, more efficient way of calculating this, using analytical approximations and a better code, and did it. And this is the first time that people actually, there's actually somebody calculated what are the actual radial profiles that are the initial conditions. Before this, people used some ad hoc profiles. So they said, okay, black holes form, let's just put some bump there or whatever. Some smooth profile, or then said, let's assume that the field is Gaussian and use the mean profile. First of all, the field is not Gaussian, and second, it's very far away from the mean. And so what we can do is we can start from the inflaton potential, and then from first principles, calculate what is the density distribution of each of these patches and what is the compaction function as a function of radius. So the idea is just that we take one of these patches, and instead of calculating it for one scale, we calculate it for several scales. So we have these 10 to the 4 momentum shells for every one of them, and then we use we just use the inverse Fourier transform, assuming spherical symmetry, and just calculate the radial profile from these 10 to the 4 momentum shells, and then repeat this for a large number of patches. So, we had and then we, from the knowing this curvature perturbation, then we can calculate the compaction function to know everything about the radial behavior, and then we repeat. Here we didn't actually have 10 to the 11, we have 10 to the 9 patches to get statistics for the compaction function. This is an example of what things look like. So this is one realization. I know there's too much stuff on this plot. This is basically the radius from the center. This is the curvature perturbation is this yellow line, so we have these small fluctuations. And then this compaction function which is the mass excess, is basically a derivative of this. And then it's the first derivative, and then it's lots of fluctuations. These fluctuations are physical. These are not noise. I mean, they're quantum noise, but they're not computational. And so if you compare, this is the Gaussian case where we see that the maximum of at the origin, the curvature perturbation is the same. So in Gaussian profiles, typically you start smoothly, and it's like this. So if you assume that the field is Gaussian, then you can analytically calculate the mean profile. And then the compaction function looks like this. And in the real case, you have these quantum fluctuations, so you have lots of noise, and the compaction function here is higher. But of course, you understand that if you have something smooth and then you have lots of noise, you can go up or down, and you're asking, do I exceed the threshold? Of course, you have more things that exceed the threshold. So this is what it actually looks like. So this is completely different from the profiles that have been used to discuss black hole collapse before. And now this also means that now we can also calculate the black hole mass. So we don't have to assume, okay, 20% of the of the Hubble patch goes into a mass. So this goes into your question about the mass, because now we say this is where the compaction function is 0.4. So all of the mass inside this radius collapses. So once we have found the compaction function, we find the maximum. We see does it exceed the collapse threshold, and then the mass is determined on this starting from the potential going to here. It's not the thing. It's something that comes out. So we don't need to have any window function out or assume anything like this is determined. And what happens is that the mass is very wide. And again, you can easily understand because this peak can be in this position or that position. So it's stochastic. So this is the mass units of solar mass. This is what would be the peak, and this is probability. So this is where is the peak of the power spectrum. This is the scale that would give. So naively, we would expect scale of the peak of the power spectrum is where you get the kicks, and this is where you have the mass, and in fact the mass is much wider. And you see that it's like 3-4 orders of magnitude in mass. So this affects the quantum kicks push you to higher masses. And this is 3 or 4. I mean, you see that this is quite broad. You have 10%, you go like 4 orders of magnitude, which means if we actually took this and fit it here, you might have problems because this is only 4 orders of magnitude, so you can easily have excess here or here. But of course, these constraints are assuming that everything is the same mass, so you need to recalculate. But this is an issue that can happen. Then there is another effect that pushing the mass to smaller masses, which is the black hole collapse close to the threshold, is actually a critical phenomenon. So you have a critical scaling of the mass, which distributes the mass to smaller and smaller.
Why is it a critical phenomenon?
Why is it a critical phenomenon? I guess the easiest way to understand it is that so when you collapse, there is a self-similar regime in the collapse, and there is actually so there is a phase in the collapse. So if a mass density that collapses, and there is a phase when actually the mass divided by the radius of the maximum compaction function remains almost constant. So the thing is collapsing, but it's also shedding mass because pressure effects keep pushing it up. So typically what happens, you start, like if you look at the compaction function, become more compact, and then you reach this regime which is basically self-similar, because you lose mass, but you also become closer to the radius, and then you can stay for a long time in this regime, and then either collapse or not. And this is very sensitive, and so you have this sort of a critical scaling with a certain exponent that then determines the black hole mass. And I understand, of course, if this collapse goes on for a longer time, you get smaller mass. Shorter time, you get bigger mass, and this is the reason basically why you distribute what you initially thought, okay, a collapse at this scale, actually distribute the mass to smaller, black holes of smaller mass. So that effect is not included here. This is only the effect of stochastic, but that effect would push it down to smaller scales. Anyway, so just that.
So they're using this some dynamical critical exponent now for this?
Yes, it's 0.36. At least for smooth profiles. Nobody has done the analysis for the stochastic profiles. Okay. So now, earlier I noted that the exponential test gives you 5 of magnitude in the primordial black hole abundance if you use the curvature expression. But if you use this compaction function, which is the real one. So this is the compaction function. So this is the probability distribution. So we calculate the compaction function for 10 to the 9 patches. We find, what is the maximum value, and we put it here from 0 to 2/3. And this is the result of the calculation. And if you put the collapse at, say, compaction function 0.4, this is like 10 to the -7 or something. And this is the Gaussian distribution. So there are 9 orders of magnitude. So these stochastic kicks give huge correction. So the fact that you have an exponential tails gives you a factor of 10 to the 5. The fact that so that just means that there are more patches that have bigger inhomogeneities. Then there's another thing, what is the structure inside these patches? And that gives you a primordial enhancement of 10 to the 9, or if you use the average compaction function 10 to the 2. Typically these averaged, which I'm not going to explain in detail, and the basic one gives an almost same order of magnitude. This again shows that this basically we cannot trust this result, because the collapse threshold at 0.4 or 2/3 has been calibrated on smooth profiles. These profiles are very far from smooth. And what will happen also is that once you enter the Hubble radius, then these perturbations are not frozen anymore, they will evolve, and pressure gradients will obviously smoothen away. Some of the more narrow spikes probably will not survive. So we are now working with Ilya Muskov to redo the primordial black hole formation simulations and find out, first of all, how much of this enhancement survives, number one, and number two, what is the collapse threshold criterion? Is it the compaction function or something else? So nobody actually knows how many black holes now form because of this stochastic profile. And there's another issue also. We assume spherical symmetry, which is true if you look at the maximum, which is for Gaussian fields is known to be okay. If you look at very high peaks, so if you look at very high peaks, then probably you're at the maximum. They're very spherically symmetric, but these are actually random points in space. We didn't sample that we are at the maximum, so we have to consider a 3-dimensional stochastic field, not a radially symmetric. And this again requires a bit more thinking about how we do that computationally, because we cannot just say, oh, let's do everything in 3D. It's too much because you need very large numbers of samples. Okay, so primordial black holes, if they're Planck scale relics, so asteroid masses can be all of the dark matter. If you generate them in single field inflation, then you need to slow down the inflaton. If you slow down the inflaton, you get big perturbations, which means that stochastic kicks can have a big effect. And they can change the abundance by many orders of magnitude. One, because they lead to an exponential tapeout of perturbations. We have shown this numerically, this has also been shown. analytically. So you have many more patches that are big in homogeneities. And second, these same stochastic effects make the individual patches choppy. So we are the first ones who did this, which also means that the primordial black hole formation calculations need to be redone. And we also need to basically check the spherically symmetric approximation. But so there's other things that we are thinking about, we are planning that are fun to do, but let me stop here. I'm glad you said that there's no strict time limit because it looked 45 minutes past 10 minutes ago. So thank you.
Thank you very much.
Just to clarify, the patches you were referring to were patches of overabundance.
Some of them are underabundant.
I see you do both.
No. So we just take one patch and then we see does this have, what do the quantum fluctuations give us? Sometimes they're overabundant, sometimes underabundant. Unfortunately, we have no reliable way of selecting. If we could bias, I mean, there is a thing called sampling in stochastic processes where you introduce a bias in your distribution so that you sample only the things that you're interested in. We thought about it. The problem is that to do that, you have to be very well calibrated to be sure that your sampling doesn't introduce a bias in your results, and that's we didn't find that to be worth the trouble. So if you look at, for example, the compaction function, yeah, but the compaction function doesn't actually tell you the overdensity.
You're over your mass distribution there, isn't it?
Yes.
The red one is the black hole mass distribution public.
Yeah. But this is obviously calculated only from the. This is calculated only from the patches that collapse.
From the sun.
Only from the patches that collapse to form black holes. They don't form black holes. There's obviously nothing there.
So your dashed line at.
This is just where the peak of the power spectrum is. So naively we expect the peak of the power spectrum gives the mass. This is an approximation that people usually use. We find that actually the mass is on bigger masses.
So that's 10 to the minus 12
solar masses. Yeah.
So that's still quite large. So in Planck scales, it's enormous.
Yeah. The relic case where you end up with final mass of 1 Planck mass is also interesting, but that's for a number of reasons much more difficult to do. We also considered that in one paper, but it would require a lot more work.
The peak seems to be enormous, in fact. The peak seems to be enormous. I don't know for. It isn't natural to use a scale of solar masses there, whereas.
Yeah. Well, basically, this mass is just determined by where in the inflaton potential we put the. Where in the inflaton potential we put the feature. So the mass range of about 10 to the minus 12 or something solar masses is just because we have put this so that these perturbations that they exit the Hubble radius at a certain time, and when they re-enter, then the mass in the Hubble patch will be about 10 to the minus 12 solar mass. If we wanted to get relics, we would put this much closer. We would just shift this so that this feature is close to the end of inflation, so that they, for example, exit here and then they enter quickly after the end of inflation, so that say the mass inside the Hubble radius is like 1 ton, and then they radiate down to 1 microgram or something. But that's completely tunable.
It's completely tunable.
Yeah.
It's completely tunable.
It's good. Yeah. The limit of if you get it from quantum operations, the limit is that if you put it too close to the CMB region, you will spoil the CMB region. So this is if you want to do this with Higgs inflation. Actually, you can only do relics because you need to push this to the end of inflation. Otherwise, the quantum corrections will give you this will also spoil this. Of course, if you write the potential by hand, then you can do whatever.
And how large can you make it?
How large can you make what? The mass? Yeah. Then you basically observation and you're limited to 10 to the minus 11 solar masses. You cannot have more massive than that. If everything is dark matter, of course, we can have a small tail there.
But your model can give you even larger.
Yeah. Then it's, of course, if it becomes very, very massive, then more massive it is, the closer you push to the CND region. So, for example, theoretically, you could not have black holes that enter the horizon of Hubble radius at last scattering. You could have lots of mass, but then, of course, you need to have a feature there which you don't see in the CND. So that's why you need to, like, theoretically, do it a bit separate.
It just surprises me that you can get some scale that's so large from some quantum phenomena.
But there are two things. The field value here is 0.5 Planck masses. The point is, what is the wavelength of these modes? And this exponential difference is, of course, generated by the exponential expansion during inflation. So you exit here, and then these modes get stretched exponentially, so they become bigger and bigger and bigger, and then they, stretch. Inflation ends. They keep stretching because the universe keeps expanding, and then they enter the Hubble radius, and by this time, the mass inside the Hubble radius is 10 to the minus 11 solar masses, so then this is the Hubble radius. So it's the expansion of space that is generating you from these microscopic numbers, something macroscopic.
Do you know that if you were to include the 3D effects and go
Include what?
The 3D effects and go for a non-spherical
Right.
How much computing time would that add?
A lot.
Is it feasible to do, or
not for the. So we haven't started doing that yet.
You could take multiple at a time.
Right. So you could have some sort of multiple expansion. I think it will not be feasible to do this sort of sampling that we do for 10 to the 9 and so on. I think what we want to do initially is just to show that it can be done in some few cases and not to do this sampling. But we have another way, so we want to also to have a sort of analytical way of getting to this very, very unlikely phenomena. So basically we want to use extreme value theory. Because if you have a distribution of maximum, then in the limit, when you get very close to the maximum your distribution size goes to infinity, then this distribution of maxima follow some universal profile, independent of what is the underlying process. And the idea is that we can somehow fit this known profile from what we have here. And it's a bit problematic because there are certain assumptions for these profiles, that we have independent samples and so on. But basically, we want to use extreme value theory to be able to calculate deep into the tail without having to do the sampling. But that's also work in progress.
What was the reason you used Higgs inflation?
Initially? Yeah. So here, this we call Higgs inspired. So we used it here just because we already had the potential and we knew what it does. And we had already tuned it to get solar mass, really supermassive for the center black hole seeds or solar mass. Originally, we used Higgs inflation because we wanted to study this possibility that what if there's nothing but the standard model? Can you still get dark matter in a sense that if you, from primordial black holes, can you use Higgs to drive you both inflation, give the CMB and the primordial dark holes? And the answer is yes, if you have relics, not for asteroids.
How different would it be for R2 inflation?
Hmm?
How different would it be for R2 inflation?
R squared inflation. So classically they're very similar. The predictions are the same to leading order, but of course the quantum corrections are different. And I don't think anyone has done this loop because this uses 3 loops. I think we have 1 loop here in this flat region, and we have 3 loops here. And for the running. And and I don't think anybody has done this for our school. So I don't know how the beta functions running behaves. In that period.
Yeah, but your big problem is not creating that little bump. So
yeah, so this is the. So whether it's doable there, and it's really not that, oh, I just put something and I create it, because, as I said, one can do this for relics. This feature is here, but we are not able to do it for the aspects. And for R square, I don't know how this behaves, and it's quite sensitive to that.
The question was with regard to
R squared. So
that means R squared gravity. Is that what you mean?
Yes, so if you have square of the Ricci scalar,
Okay.
then the classical evolution is about the same. And if you have only the scalar field, if you have only the Higgs, if you have only lambda phi to the fourth, and then the coupling, then also you can show that at 3 level they're also equivalent. But of course, it's very for the coupling is all the other stuff that Higgs couples to, like the top quark and so on. And the top quark mass has a big role in this business because it's the running is very, very sensitive to that. Anything else?
Like it? Well, let's thank the speaker again.